Okay. Good morning, everybody. My name's Albert Guillén Fábregas, and I'm one of the conference co-chairs, along with Alfonso Martinez and Sergio Verdú. For those that were at the welcome reception last night, we hope you enjoyed it. For those that weren't, welcome to Barcelona and welcome to 2016 ISIT. So our technical program committee chairs have put together an outstanding program of which your contributions are actually at the very core. And I'm sure you have all prepared excellent talks, which will happen in these classrooms over there. We have 5 plenary talks and about 620 papers. And without further ado, I'll hand over to Yannis Kontoyannis, who will introduce our first plenary speaker. I wish you a very successful and productive conference, and I'll see you later for some announcements. Thank you.
All right, well, good morning, everyone. It is my great pleasure to open this year's ISIT, especially with the introduction of the first plenary speaker, who's a distinguished colleague of us, Elza Erkip, and a good friend. Elza is a professor currently at the Department of Electrical and Computer Engineering of the Polytechnic Institute of NYU, of New York University. Elza Erkip received the bachelor's degree from the Middle East Technical University in Turkey, and then she received the master's and PhD degree both from Stanford, where I had also the pleasure to meet her and share an office with her. And since her PhD in 1994, she has worked on problems in many different areas, primarily in multi-user information theory and communications, and in recent years with greater emphasis on wireless communications. Elza Erkip's research has been broadly recognized, and among other distinctions, she has received the NSF Career Award, the IEEE Communication Society Stephen O. Rice Paper Prize, the IEEE ICC Communication Theory Symposium Best Paper Award, and the IEEE Communication Society Award for Advances in Communication, and many others. She's an IEEE Fellow. She has been elected a member of the Science Academy Society of Turkey. She was a distinguished lecturer of our society a couple of years ago, and she's a very well-cited author. She's among the Thomson Reuters highly cited researchers. There are more I could mention, but I will be brief, and I'll just say that she has also been very generous with offering her time in the service of our society in many roles. She has been a member of the Board of Governors since 2012, where she's now, I think, second vice president. And she has been an associate editor and a TPC chair and a TPC member in more meetings than we have time to mention right now. So I'll just, yes? I will talk much more slowly then. And it is good that I have only one last sentence to say. That today we have the pleasure to have Elza Erkip talk to us about the theory and practice of cooperation in wireless networks from 3T to 5G. Elza, thank you very much.
Okay. Good morning, everyone. Can you hear me better? How is it? Okay, very good. Thank you very much for the nice introduction. It's a pleasure and an honor to be the opening act of this ISIT, which is taking place in this wonderful Mediterranean city of Barcelona and in this wonderful location. It's especially priceless to be introduced by my old friend and former office mate, Yannis. I'm a faculty member with NYU Tandon School of Engineering, which you may know as NYU Poly or Brooklyn Poly. I'm also a member of NYU Wireless Research Center, where we do many investigations of fifth-generation of wireless networks. And today, I want to tell you how we got in information theory and in wireless from 3 terminals to 5G. But before I start talking about the technical aspects of 5G, I want to give you a brief snapshot of how the popular media use 5G. OK, let's see. Is this working? Let's see. This is part of the act. I'm going to click. OK, good. OK, so apparently, New York Times thinks that wireless is still in the 90s. It's about men in suits talking on their phones. But we know that wireless is much more. Luckily, they've been able to capture the essence of 5G in their text, where they talk about 5G meaning downloading movies in seconds, networks with many, many devices, and extremely fast response times for applications like autonomous driving. And indeed, on the regulatory front, there's been a lot of hype recently. There's an upcoming vote by FCC in the US on July 4th. And this vote is about making millimeter wave spectrum available for 5G. And this is coming before the standards are in place for experimentation and evaluation of various 5G technologies. And of course, European press talks about 5G as well. Particular, in Spain, El País has been reporting about 5G. I don't think you need much of Spanish to understand that they're talking about mobile phones and 5G. That's the extent of my understanding. OK. Now, it's very kind of encouraging that for us engineers, something that we work very closely with, such as 5G, is covered so widely in the press. But from engineering perspective, what exactly is 5G? What are some of the promises of 5G, and how are we going to be able to achieve those? One thing that is envisioned for 5G is having much, much higher data rates, about 1,000-fold improvement over what we currently have. And that is going to be brought forward by combination of many advanced techniques and resources, such as making spectrum much, much wider. This could be as a result of combining licensed and unlicensed bands, or as in the case of FCC vote, making millimeter wave available where there's a very wide bandwidth to be used. It also hinges on more infrastructure density, as in the case of small cells, many, many more antennas, as in the case of massive MIMO, much higher spectral efficiency through a combination of various methods, one of which is full duplex. But 5G isn't just about higher data rates. It's also about lower delay, maybe a 10-fold decrease in delay. And again, some of the technologies that are envisioned to bring about this substantial improvement is an integrated design of the core network and the protocol stack, such as done in software-defined networking, or moving intelligence, computational power, and storage much, much closer to the end users, to the edge of the network, as done in foreground. But 5G isn't just about mobile phones and a single application. It consists of a combination of devices and applications. Of course, mobile broadband is an important application, but also applications that connect millions of machines, as in the case of Internet of Things, and very fast and reliable communications, such as the ones needed to enable vehicular networks and autonomous driving. OK, so these are all great from an engineering perspective. But we're at an information theory symposium, and what does all of this mean for an information theorist? And where is information theory in all of this? And I'm going to claim that it's everywhere. It's already in a lot of places, and it potentially could be in a lot more. And information theory is crucial in getting 5G to where it wants to be. To give you a few examples, in information theory, we know how to study wideband channels, which is essential in understanding what to do with the abundance of spectrum. Obviously, MIMO and massive MIMO was all started in information theory. Multi-user information theory is in a variety of places in 5G, where we should figure out how to deal with interference if we're going to go for higher infrastructure density, full duplex nodes, which create additional interference. But also, as we move intelligence to the edge of the network and maybe cache part of the information at the edge of the network, we need to use multi-user information theory ideas to figure out good strategies. And different type of networks, as in Internet of Things and vehicular networks, will all make use of information theoretic principles. And last but not least, distributed compression and joint source channel coding techniques will be essential in understanding what happens when we store parts of information across the network, how to best deliver information in the presence of partially cached information. And many sensors that we see in IoT type of applications and vehicular networks is going to require us to better use principles from distributed compression and joint source channel coding. OK, so what are some of the opportunities that are coming up for information theorists in 5G? Now, obviously, all these new technologies and new applications will allow us to come up with new models and new theories. But it's not just that. Some of the old techniques that we're all familiar with, but maybe we thought that would never be practical, can now be practical because of the abundance of computational power, cheaper storage devices, higher degrees of freedom. Now, in today's talk, I'm going to try to make these two cases in the context of cooperative networks. And I'm going to very loosely define cooperation as terminals helping one another communicate. There's also the source coding side of cooperation, but today's talk is mainly going to focus on the communication aspects. And as with every talk, this is going to be a biased talk, biased towards my own experience and understanding of cooperative communications. And in fact, it's going to trace my own professional and personal journey from 3 terminals to 5th generation. I started learning about 3-terminal networks and the relay channel and various interesting problems in multi-user information theory when I was a PhD student in California. Then I spent a few years in Texas, where I started applying my knowledge to model cooperation in wireless networks, which I continued doing after I moved to New York. And more recently, I've been working on 5G applications. Now, in the process, my haircut changed from a bad student haircut to a much shorter one. And I think I've acquired more than a few strands of gray hair. And I hope that I've acquired a little bit of wisdom. And my hope today is to pass along some of that wisdom to you. I've intentionally kept the talk low on equations and math. And there are only a few key references. These were the references that helped me understand the material. And I apologize in advance to the many, many authors whose work is not cited here today. OK, so what's the rest of the talk going to be like? So I'll first start by giving an overview of theoretical foundations of cooperation. Some of the groundbreaking work that happened in the 70s and the 80s. I call this generation X and Y of cooperation. And even though we know that generation X and Y are by no means old, my teenage daughters like to say that these are oldies but goldies. And then I'm going to move to the extensions of theory, which mostly happened in late 90s and 21st century. This is the generation Z of cooperation. And most of these extensions were driven by wireless applications. And then finally, I'm going to touch upon some of the applications in 5G. You could call it generation alpha of cooperative networking. So first, some of the theoretical foundations, oldies but goldies. Now, it all started with this paper of van der Meulen in 1971 called Three-Terminal Communication Channels. This was the first occurrence of cooperation in information theory. And van der Meulen looked at a communication scenario where a terminal T1 wishes to communicate with a terminal T2 with the help of a third terminal he called T3. Then about 8 years later came a big landmark paper by Cover and Gamal. This is how they looked back then, entitled Capacity Theorems for the Relay Channel. Now, this has been a seminal paper with many, many key results that we still use today, a number of achievable schemes, an upper bound, and capacity in some special cases. So I'm going to spend a little bit of time going over some of the essences of this paper, which to this day are very relevant in research of cooperative communications. Now, so what is the relay channel like? Very simply speaking, it's a relay helping a source and a destination communicate, and it encompasses some important communication modes that we investigate in information theory, namely broadcasting from the source to relay and destination, and multi-accessing from the source and relay to the destination. So as such, relay channel brought together a number of ideas that were used in these components earlier. Now, some of the model assumptions that were used in Cover and Thomas, and we still use these assumptions to date. Of course, the relay is causal. The relay cannot look ahead. And the relay is full duplex. That is, the relay can receive and transmit at the same time in the same frequency. Now, I'm going to talk later about this full duplex assumption, whether it's practical or not, and what has happened since then. But for now, the relay is full duplex. And it was observed that in the Cover and Gamal paper that capacity of the relay channel is not known in general, and they found the capacity only in some special cases. Obviously, this wasn't because these weren't capable authors, because the problem turned out to be very difficult. And to this date, we don't have a complete characterization of the capacity of the relay channel in its most generality. But we do have a number of very important results. Cover and Gamal obtained a cut-set upper bound in a number of achievable schemes, two of which I'm going to show you today. The first scheme that I'm going to talk about is decode and forward, in which case the relay helps the destination by fully decoding the source information. And then the relay re-encodes the source information in such a way as to cooperatively transmit with the source. This resolves the ambiguity and the destination can finally decode the source information. It was shown in Cover and Gamal paper that decode and forward is optimal for the physically degraded relay channel. Intuitively, this is the case when the relay has physically a better quality signal than the destination. And obviously, in that case, imposing a decodability constraint at the relay does not really limit the performance and the rate of this channel. Another important strategy that was introduced in the seminal paper was compress and forward, in which case the relay simply looks at the signal that it has observed, the output of its channel, quantizes it, and sends it to the destination. But during this process, realizes that the destination also observes a channel output that's correlated with relay's channel output. So this compression can be done in a more efficient way using distributed compression techniques, such as Wiener-Zev. Compress and forward turns out to be a very good strategy when the relay to destination is of high quality. Again, intuitively, this is because, in that case, the quantization noise that the relay introduces is very small. Now, many authors have worked on compress and forward, and a few major improvements to CF were made, though this came much later, inspired by deterministic models. Quantized map and forward was put forward, and noisy network coding was introduced. And these two schemes and others turned out to be very suitable, not just for the simple relay channel, but for relay networks when we have a lot more terminals in the picture. OK, so another important contributor was yet another Dutch master, Frans Willems, and his work in the 80s. Frans was a student, PhD student of van der Meulen, and he introduced a number of important models and techniques that led the way in further research in cooperative communications. In particular, he investigated a multiple access channel in which the sources can cooperate in various ways. This could be through cribbing one another's input, or conferencing, or through some generalized feedback that they receive from the destination. Okay. So now this was some of the foundations of cooperative communications. And then we fast forward into late 90s and early 21st century. And in fact, in between the 80s and late 90s, the results in this line of work weren't as many. I think partly because it felt like this was a mature field. But once wireless applications started taking hold, researchers realized that a number of principles that were introduced earlier are useful in wireless. And also a number of new models came about, and there was an explosion of research starting from late 90s. And like the actual Generation Z, a lot of this research was driven by wireless applications. Now, in covering this research, I'm going to briefly touch upon different areas, such as what was done in the wireless channel with respect to cooperation, incorporating some practical constraints, such as half-duplex, what happens when you put more users, more relays, and what happens when you look at large networks, as in the case of large cellular networks or large ad hoc networks. So I'm going to start by talking a little bit about the progress that was made in cooperative networking with respect to wireless channel and incorporating practical constraints. Now, in late 90s, early 2000s, it was recognized that the simple relaying action or cooperation can, in fact, mitigate fading in a wireless channel and create diversity. This went under different names, such as user cooperation diversity and cooperative diversity. And this, for the most part, motivated not only information theorists, but also wireless researchers and communications researchers to study cooperation in the context of wireless communications. And it was around this time that the scope started to expand beyond information theory, and other researchers started to get interested in the notion of cooperation and relaying. Just to give you a brief insight about how diversity comes about in a simple relay channel, let's think of kind of the simple diagram. There are 3 links in this network. Now, if only one of the links fail, if you just remove one of the links, you're still going to be able to find a path from the source to the destination. However, if you cut 2 links, if 2 links fail, then transmission may fail. This intuitively suggests that diversity is 2, and this is the same diversity as a 2-antenna source. So the source and relay can now form a virtual antenna array, if you will, even though they're connected by a fading link. Okay, so this was the main observation beyond obtaining diversity through relaying and cooperation. There was also a lot of work incorporating some practical constraints, such as the duplexing constraint. As I mentioned earlier, the original paper and the earlier papers on information theory, and even to this day, assumed that the relay is full duplex. Okay, so this was a common assumption in information theory literature. But when we looked into practice, people realized that transmit and receive signals are about 100 dBs apart. And when they sit on the same device, it's very hard for the receiver circuitry to be able to eliminate the self-interference coming from the transmitter circuitry. And that resulted in people, in researchers looking at half-duplex constraints. But I'm going to come back to this full-duplex constraint not being practical. And in fact, we're going to see that very recently, many groups have been able to build full-duplex radios with enough self-interference cancellation. But for now, in the late 90s and early 2000s, many of the assumptions that looked at cooperative communications started incorporating this half-duplexing constraint. Half-duplex suggests that the relay cannot transmit and receive at the same time, so has to do one or the other. And there's been a lot of works in adapting the strategies that we looked at earlier, decode and forward and compress and forward, to work with half-duplex relaying. This wasn't by any means a trivial task. And also, simpler strategies such as amplify and forward, which apply for the Gaussian channel, were shown to be very effective. Now, all of these strategies, if you do it right, you're able to improve the diversity of the system. But unfortunately, because of the half-duplexing constraint, this came at the expense of some loss in spectral efficiency. So there's no free lunch. And many groups looked at how one can trade off diversity versus multiplexing gains in cooperative systems, and what are some of the strategies that give us the best trade-off. OK, so next I want to briefly talk about cooperation in multi-user channels. So far, we've looked at a scenario with single source, single destination, and single relay. Now, multiple relays were thought about in the context of this parallel diamond relay channel, starting from 2000s. And you can use these multiple relays in a variety of ways. For example, if you have a bunch of relays that can decode the source signal, then they can act as antennas of a multi-antenna transmitter and transmit signals that belong to a space-time code. This was called distributed space-time coding. Alternatively, if the relays have a lot more information about their channel towards the destination, such as phase information, and you're able to synchronize them reasonably well, they can actually do distributed beamforming, giving a lot more gains. OK? But also, relaying and cooperation was introduced into various multi-user network models. For example, you can think of a multi-access channel that's aided by a relay. You can think of a broadcast channel that uses the help of a relay. Two-way channel can obviously make use of a relay. An interference channel can be aided by a relay. Now, don't think that because I'm kind of going through them fast, the work in these areas was trivial. But what I would like to show you is kind of some of the new ideas, beyond decode and forward, compress and forward, and variations that came about once people started investigating relaying in multi-user scenarios. And the first idea that I'm going to mention pertains to multiple access relay channel and two-way relay channel. It was observed that if the relay is working in the decode and forward mode, the relay does not really have to decode each source individually. Maybe the relay can decode functions of source messages and forward them to respective destinations. As long as the destinations can uncover the information, we'll be OK. Now, this went under various names: analog network coding, compute and forward. And one important observation was that random coding in such scenarios may not be enough, and we may need to resort to structured codes. Another set of ideas came about when relaying was considered in the context of interference channel. For example, in the simple Z interference channel, the relay cannot help by forwarding useful signals, but it can certainly help in mitigating interference. It can try to cancel interference at D1, or it can forward interference so that D1 can decode interference and strip it off. So this turned out to be also useful in arbitrary interference channels with relaying, where signal forwarding, and interference cancellation turned out to be useful strategies. OK, so before moving into 5G, I want to briefly mention cooperation in much, much larger networks, cellular and ad hoc networks. In the case of cellular networks, the main mode of cooperation that has been studied is cooperation of base stations. And these base stations can cooperate because they're connected to the central processor through finite capacity links. potentially different for uplink and downlink. But nevertheless, this kind of connection to the central processor allows the base stations to cooperate. And this cooperation can come about in different forms. If the base stations have baseband processing capability, they can actually decode and forward. And in that case, the links connecting them to the central processor are called backhaul. And in fact, this has appeared in 4G LTE standards under the name of coordinated multipoint. Alternatively, if the base stations do not have baseband processing capability and it's done centrally at the central unit, then these links are called front haul, and soft information has to be forwarded back and forth, as in the case of compress and forward. And this goes under the name of Cloud RAN in the literature. OK. Now, the notion of base station cooperation allowed researchers to put together many, many ideas coming from different sides of information theory, from Wiener cellular model to multi-user MIMO channels to multi-user cooperation, not only to mitigate interference, intercell interference, but also to exploit it to their advantage. In the case of ad hoc networks, a seminal paper by Gupta and Kumar in 2000 recognized that if we're looking at a large ad hoc network, rather than trying to find the exact capacity, we could look at how capacity scales with the number of users. So this goes under the name of scaling laws, and it was recognized that multi-hopping is essential for communication among distant nodes. There's been many, many, many extensions to the original work of Gupta and Kumar, improving how nodes cooperate. One particular mode of cooperation that is hierarchical cooperation turned out to be really valuable in terms of improving the scaling laws. OK. So now, I'm going to move forward into 5G and show you in a couple of examples, and these are kind of simple examples, how in 5G, relaying and cooperation can be potentially much, much more useful. And I'm going to start by looking at relaying in 5G. And then I'm going to move on to some of the recent practical full-duplex designs and how they can be used in a cellular network in conjunction with base station cooperation to result in improved rates for cellular users. Okay? So first, relaying in 5G. But before relaying in 5G, I'm going to talk about relaying in 4G to give you an overview. Now, the good news is that in 4G, relaying has made it to the standards. It's in a very simple form, as in the case of multi-hopping, in which case the destination does not hear anything from the source. But relaying in 4G has been used for a variety of tasks, for mitigating shadowing, for increasing throughput in hotspots where there are a lot of nodes, or for increasing coverage of the cell. Furthermore, this isn't just kind of a concept that's sitting out in the standards. There are some practical applications of it, such as Sprint being rumored to acquire relays to extend coverage and throughput in hotspots. There are products that are being sold, such as this one from Airspan. It's a 4G LTE relay to increase coverage in hotspots. So it's not just in the standards, but it's also appearing in practice. Now, this is all nice for us information theorists, but there are still some issues with 4G relaying. And the issues have been that 4G is very limited in its degrees of freedom. So spectrum is very scarce. The number of antennas are small. Furthermore, relaying is done in a half-duplex fashion, where we further lose degrees of freedom. Now, relaying is effective for power chain, but because we have to give up degrees of freedom for it, its net impact on the throughput in some scenarios may be limited. Okay? But as I'm going to argue today, with 5G, this may all change. Intuitively, why? Because we have an abundance of degrees of freedom. We have a lot more spectrum, a lot more number of antennas that would facilitate relaying. Furthermore, there are full-duplex implementations that would allow us to go beyond half-duplex relays. So what I'm going to do today is I'm going to talk a little more about abundant degrees of freedom in the context of multi-hop relaying. Okay? But before we talk about abundant degrees of freedom in relaying, I just want to step back a little and think a little bit about how we use spectrum and bandwidth in a point-to-point channel. Okay? So this is a very simple point-to-point additive white Gaussian noise channel. And this is the famous Shannon capacity formula everybody knows. Okay? Now, when we look at capacity as a function of bandwidth, and we think about low signal-to-noise ratios, we realize that capacity is proportional to P over N naught, which suggests that no matter how much improvement we have in bandwidth, we're not really going to see much effect on the capacity, and the capacity is power limited. So instead, we should work on improving the received power. On the other case, in high SNR regime, capacity is directly proportional to bandwidth, and the system becomes bandwidth limited. Hence, we should put all our efforts in improving the bandwidth of the system. Okay? So this is very clear in a point-to-point scenario. But it may not be so clear what's happening in a cellular network. So when does a cellular network become power limited or bandwidth limited? And in particular, what is the role of relaying in overcoming some of these limitations? So I'm going to tell you a little bit about some recent work that we've done that uses capacity scaling as a metric and incorporates bandwidth into the formulation and looks at mainly cellular scenarios. Again, the strategies aren't very complicated, but I hope that I'll be able to give you some insights about how relaying would potentially perform in a 5G system where degrees of freedom are abundant. Okay? So what we're going to do is we're going to look at a cellular network with a cellular type of traffic where the traffic flows uplink from mobiles to base stations and downlink from base stations to mobiles. Okay? So there is no ad hoc mode of communication. All the traffic has to go through the base stations. I'm going to assume that we have a lot of networks, a lot of nodes in the network that are uniformly distributed in an area that also scales with the number of nodes n. This area is served by m base stations that are uniformly placed in the area, and the number of base stations also scale with the number of users n. Each base station has L antennas, which again scales with the number of users. And by playing with these scaling exponents, we'll be able to uncover some results in different regimes. We'll assume that the base stations do not cooperate. I'll talk about base station cooperation a little later. And finally, we also assume that the bandwidth scales with the number of users. And we'll see the effect of bandwidth scaling on performance, and in particular on performance of single hopping versus multi-hopping. Okay? We're mostly going to focus on downlink today, though you can get similar results for uplink as well. So how do we figure out how the throughput in this network, rate per node, scales as the number of nodes increase? Well, to do this, we first look at a cut set bound. Very simple cut set bound. We look at cut around each base station. Remember, each base station has L antennas. So this cut results in a MIMO system that is L by N. But all of the receivers are at different locations because of path loss. It takes a little bit of analysis, not very difficult, to compute this upper bound and figure out how this upper bound scales as the number of users increase. Okay? So that would be our throughput scaling upper bound. I'll show you how that behaves a little later. We can also envision two very, very simple schemes, inspired by what's done in cellular systems and what could be done in cellular systems. The first one is infrastructure single hop. The other one is infrastructure multi-hop. Why I call them infrastructure? To distinguish them from their ad hoc counterparts. Again, all the traffic has to go through the infrastructure. So what happens in infrastructure single hop? As the name suggests, the base station simply transmits to all mobiles in its own cell. Base station has L antennas, so divides the users into groups of L, within each group can do L by L MIMO broadcast channel principles to serve all of them at the same time. And each group is given an orthogonal frequency, okay? And then there's out-of-cell interference that's treated as noise, okay? So again, when you consider the fact that all mobiles could be at different distances, you can compute the throughput scaling that's achieved by single hop, okay? I'm not going to show you the formulas. Now, similarly, multi-hop, well, in this case, the traffic is going to flow from base station to the end mobile in a multi-hop fashion. And in order to enable this, we've divided the cell into routing subcells, the sizes of which are adjusted to maximize the throughput scaling. And the base station, by virtue of having L antennas, initiates L routes simultaneously, and then traffic is forwarded in a multi-hop fashion from routing subcell to routing subcell until all nodes are served. And again, out-of-cell interference is treated as noise. Okay? So we can again compute how the throughput of multi-hopping scales with the number of users n. Okay? So instead of giving you the formulas, I'm just going to show you some plots explaining our results. But I'm not even going to kind of, so I want you to forget this plot for now. I mean, there seem to be too many, phis, betas, gammas. I'm going to walk you step by step and point out important operating points in this plot, OK? So forget this. OK. So let's look at first what happens or what potentially could be the case for 4G. Okay? Now, this plot shows in the horizontal axis how bandwidth scales with the number of users. So it's the bandwidth scaling exponent. Okay? And in the vertical axis, it's the scaling exponent of rate per user as the number of nodes in the network increases. Okay? And in 4G, as we saw, degrees of freedom are limited. Spectrum is scarce. So we're going to envision, we're going to model that scarce spectrum as having a bandwidth scaling exponent of 0. So we're going to assume that the bandwidth does not increase with the number of users. Okay? So we're operating at the origin. Okay? And that tells us that the rate per user scales with an exponent given by beta plus gamma minus 1. Now, well, what was beta and gamma? Well, beta was the scaling exponent of base stations. Gamma was the scaling exponent of the number of antennas. And any reasonable practical system wouldn't put more infrastructure than number of users. So we assume that beta plus gamma is less than or equal to 1. And remember, these base stations are connected to the back hall with fiber optics. So you don't want to put too many base stations either. Okay? They're expensive. But this suggests that at this operating point, beta plus gamma minus 1 is negative or cannot be positive. And rate decreases, or in the best case, is constant as the number of nodes in the network increases. Okay? And more infrastructure means slower increase, but nevertheless, the rate in the network cannot increase with the number of nodes. Furthermore, single hopping is optimal. Well, so is multi-hopping, but multi-hopping is not necessary. Okay? So this may partly explain why in 4G we don't see too much benefit from multi-hopping in terms of increasing the throughput of the network. Okay? So now let's see what happens in 5G. Okay? So with 5G, we're going to have an abundance of bandwidth. So we're going to envision that bandwidth potentially increases as the number of users increase. So now we're moving along the horizontal line of this plot. Okay? And initially, for a certain regime, single hopping meets the upper bound and hence is optimal. Okay? And in fact, single hopping becomes optimal until a node at the edge of the network becomes power limited. Right? Remember, single hopping just goes to that node directly. Once that node at the edge becomes power limited, single hopping cannot exploit the increasing bandwidth anymore, and the rate scaling exponent becomes constant. Okay? Now, what about multi-hopping? Well, with multi-hopping, one thing that we see is that this simple multi-hopping protocol always meets the upper bound. Okay, so it's multi-hopping is always optimal. Furthermore, both the network and multi-hopping are able to exploit the increasing bandwidth for larger ranges of the bandwidth scaling exponents. So multi-hopping and network is bandwidth limited for a higher scaling of the bandwidth. Now, of course, after a while, both the network and the multi-hop stop increasing their rate exponent, in which case the network becomes power limited. And this happens when the nearest node in a network becomes power limited. Okay? So in essence, the network is able to exploit bandwidth for a much longer period. Now, what about the multi-hopping gain over single hopping? This is, of course, more pronounced when bandwidth scaling is larger. And this multi-hopping gain, 1 minus beta, is higher when we have fewer base stations in the network. Okay? So again, putting base stations is expensive, and obviously, if we want to put fewer base stations, we have to make up for it by using multi-hopping. Okay? So some of these protocols, again, these are simple protocols, can be extended to incorporate infrastructure relays. So rather than multi-hopping through the nodes, you can envision multi-hopping through infrastructure relays, where the connection is, again, through wireless backhaul. And one can even envision a kind of infrastructure version of hierarchical cooperation, which in this case doesn't turn out to be very useful. The main reason is all the traffic has to go through the base station. So we're not getting as much benefits as in the ad hoc case. Okay? Now, what about base station cooperation? Well, a simple cut-set bound, considering all base station, shows that there's potentially room for improvement. But of course, one has to develop protocols for limited backhaul, front haul, when you have base station cooperation, and see whether indeed this gap can be tightened. Okay? So that's all I had to say about relaying in 5G. Again, this was a simple example, but it showed potentials of multi-hopping when you have abundant degrees of freedom. Next, I'd like to talk a little bit about full-duplex, how you would do full-duplex cellular, and what would be the impact of base station cooperation. Okay? So first, a bit of good news. Well, the information theory assumption of full-duplex is finally practical. So there are a number of groups around the world that have been able to mitigate self-interference. That's the interference that leaks from the transmitter circuitry back into the receiver circuitry. So they've been able to mitigate it enough to make full-duplex communications work. That's really a great news. Now, how is this done? Through various forms of cancellation at the receiver, such as analog and digital cancellation, using polarization of antennas or antenna separation. There's still some kind of residual interference, but it's at a much, much lower level, and we can live with it for at least some applications. But don't think that this is just experimentation done in the labs of researchers. There are also attempts to commercialize full duplexing, as is done by a couple of Stanford professors. Okay? But then what does full duplex mean for us information theorists? We've always been looking at full duplex, so does anything change for us? And as I'm going to show you, it may. Okay? So what we're going to do is we're going to look at full duplexing in the context of cellular networks. So first, the regular half duplexing, right? So a half duplex cellular network operates uplink and downlink in a time division duplex or frequency division duplex mode, right? What about full duplex? So we're going to envision that the mobiles are still half duplex. They're much simpler. But suppose the base stations had some full duplex capability. What would happen? Well, in this case, you immediately realize that there are all these additional sources of interference that arise, shown by the red lights, red curves, okay? So there's self-interference at the base stations. There's a downlink-uplink interference that a downlink transmitting base station causes at another base station that's receiving from uplink. There is uplink-downlink interference from mobiles. A mobile that's transmitting uplink causes interference at a mobile that's receiving downlink. And this could happen across cells or it could happen within the same cell. It's especially dangerous when it happens within the cell, because this could happen, you could have interference from a very nearby mobile that's transmitting uplink when you're receiving downlink. So it's very important to take care of that interference, as I'm going to show you a little later. Okay? So we've recently looked at this in the context of a cellular network when base station cooperation is enabled. And we've assumed that the central processing unit does all the baseband processing. Hence, these links that connect the base stations to the central processor are all used in the compress and forward mode to send soft information. And I'm going to show you, again, this is a simple study, but I'm going to show you how this full duplex interference plays a role in affecting the throughput, and what are some simple ways of mitigating that full duplex interference, in particular using base station cooperation. Okay? So this plot shows you in the horizontal axis the front haul capacity, the capacity of the links connecting base stations to the central unit. So the higher, the better, of course. And in the vertical axis, equal uplink downlink rate. Okay? And we have 4 curves, half duplex and full duplex, single sound processing, and base station cooperation. Okay? So essentially what we have, the first thing we observe is that when you look at the incremental gain from base station cooperation in half duplex and compare it with the incremental gain from base station cooperation in full duplex, you see that under the case of full duplex, base station cooperation is more valuable. And why? This intuitively makes sense, because now that the base stations can cooperate, the downlink uplink interference that's among the base stations can be mitigated. Right? So this suggests that if you're going to use full duplex base stations, it is worthwhile doing it in conjunction with base station cooperation. Okay? Otherwise, your gain is a lot more limited. And in obtaining these curves, remember this intra-cell uplink downlink interference that the mobiles that are close to one another are causing. We dealt with it using successive interference cancellation at the mobiles. And I'm going to just tell you something very little about successive interference cancellation. But I have one more plot to show. So in fact, this is the exact same plot, equal rate as a function of front haul capacity. And I want to point out the impact of full duplexing. So we see that the net gain of full duplexing is about factor of 1.7. It's not this ideal factor of 2 that we were hoping to get. Now, why? Because among neighboring cells, we still have inter-cell uplink downlink interference. Okay? That's partly mitigated by base station cooperation. Nevertheless, some of it remains, and it causes a loss in performance. But I think this is still pretty good, much better than a factor of 1. Okay? So, this is something worth thinking. And finally, what about successive interference cancellation? It may be complex to do successive interference cancellation at the mobiles, but we observe that as you look at the SIC curves, without SIC, the performance isn't good at all. So this plot shows in the horizontal axis the strength of intracell uplink downlink interference, and in the vertical axis, equal rate. So you do need successive interference cancellation to get any of these benefits. Okay? But an alternative could be user scheduling, where you don't schedule mobiles that are close to one another to transmit in uplink and downlink at the same time. So, so that means we need to require, this model needs to consider some of the scheduling aspects as well in order to make it more practical. Okay? Okay. So today, I wanted to tell you a little bit about 40+ years of very rich theory, many, many different applications of cooperative communications, starting from 3 terminals and moving into 5G. And I hope I've convinced you that 5G brings in new opportunities, and even some of the very, very simple strategies that we work with in information theory could potentially make big impact in 5G when thought in the right manner and when some of the practical constraints are incorporated. So what's next? For researchers, for many of the researchers here, well, there are still many, many open problems in cooperation and relaying. Some of them are very difficult, but some of them are being cracked as we speak. But there are also new problems inspired by technology, and also some of the old techniques that we've been using and we never thought could be practical can now be practical. But of course, the work doesn't stop there. We still need to think about which techniques could be used in which context, what are some of the practical constraints, and how can we make some of our old techniques work. For the engineers in the audience, and I suspect there are very few, I wish there were more. We could, information theorists and engineers could certainly benefit a lot more from interactions. But there are many graduate students here, and I suspect many of them will go and work as engineers. So I hope I've convinced those students that many advanced technologies that we see in wireless systems are rooted in information theory, in multi-user information theory, particularly cooperative communications. An information theoretic style of thinking allows you not to accept status quo and dig deeper, look at more fundamental models, try to understand benefits of different technological advances, and innovate. Now, I've heard recently of a Caltech graduation speech of Atul Gawande, one of my favorite authors. He's an author and a surgeon and a researcher. And he suggested that even more than what you think, how you think matters. So I think our goal in our research, in educating PhD students, even undergraduates, is to teach them how to think, how to model communication systems, particularly in the context of information theory, and how to understand the essences of different strategies. Now, the particular techniques that we're using and the particular results may come and go as the technology changes, but I think the fundamental understanding and fundamental thinking will stay. So with that, I'd like to thank my own PhD advisor, Tom Cover, for teaching me how to think, and for many, many collaborators and students with whom I've worked on various aspects of cooperative communications. They've certainly taught me how to collaborate and how to be a better collaborator. So with that, I'll end. Thank you. That's either good news or bad news, no? Thank you. Thank you. Thank you.